Hello everyone. What I'd like to do now is follow on from where I left off in my previous video, in which I started from the heavily damped solution to the equation of motion for a harmonic oscillator, and took a limiting case of that to show how we can derive the critically damped solution. And now in this video I'm going to start from the lightly damped solution, and again take a limit of that, and show how we can recover the critically damped solution from the opposite direction. And for some context, it would be a good idea to watch the last few videos I've made on this topic first. And so we're going to go straight into the maths here for this video. So I've got the equation of motion we're looking at the top, okay, which we've seen a couple of times before, which is x double dot plus 2 gamma x dot plus omega naught squared x is 0, where a dot is a time derivative. And the solution of this you find by just trying a solution proportional to e to the lambda t, and when you plug that into your equation of motion, you find that lambda has to be minus gamma plus or minus the square root of gamma squared minus omega naught squared. Now, the lightly damped case is what you get when gamma is less than omega naught, right? So when gamma is less than omega naught, and you can see that what's going to happen there is the stuff under the square root is going to become negative, and when we take the square root of a negative number, we get an imaginary number. So lambda is going to be complex. It's going to have a real part and an imaginary part. And so I'm going to, for notational convenience, write lambda as minus gamma plus or minus I times omega, where omega is equal to the square root of omega naught squared minus gamma squared. Okay, and the reason for defining this omega will become clear just now, because it turns out that when you go through a bit of algebra, you've got your solution as e to the lambda t, and you've got two different lambdas, right, given by this expression here. If you add those together, you'll find that your solution, x of t, x is a function of time, is e to the minus gamma t times a cos omega t plus b sine omega t. Okay, and so you can see it was convenient to define this omega because that ends up being the angular frequency of these cosine and sine terms we get in the solution. So let's figure out what these constants a and b are, right? So at the moment these are just arbitrary constants of integration, but to figure out what they actually have to be, we can plug in some initial conditions. All right, so firstly I want to, because we can have initial conditions for the displacement x and the velocity x dot or v, I want to first just work out what x dot is given this solution x. All right, so x dot as a function of t, well, we're going to use the product rule, so we're going to first differentiate the e to the minus gamma t and just get minus gamma times the rest of this stuff that we started with. Okay, so b sine omega t, and then for the next term we're going to add on this e to the minus gamma t and differentiate the stuff inside the brackets this time. Okay, so we're going to get minus omega a sine omega t, and then plus omega b cos omega t. And then we can collect all of these terms together and write that as e to the minus gamma t multiplied by, so let's collect all the cos terms together first. So the cos terms are going to be, so we've got our minus gamma a from this first bracket, right, minus gamma at the front, and then a in front of the cos omega t, so minus gamma a, and then from the second pair of brackets, square brackets, we get a plus omega b, alright, and that's the cos term. And how about the sine term, where we've got minus gamma b from the first brackets, and then we've got minus omega a from the second brackets. And so they're both negative, they both have a minus sign in front of them, so we can pull out that minus sign and write that as gamma b plus omega a, and all of that times sine of omega t. So let's now apply our initial conditions. So if we have some initial displacement, so x at a time of 0, when t equals 0, x is equal to just x naught. If we take our x of t here and just plug in t equals 0, well, e to the 0 is 1, right? So the thing in the front is just 1, and then the sine terms disappear, sine term disappears, and you just get a times cos of 0, and cos of 0 is 1. So you will simply find that x naught is equal to a. So we've already found that the constant a is purely determined by the initial displacement. So now we can apply our initial condition on the velocity. X dot of 0 is, let's say, v0. And then we want to be looking at this expression down here that we derived just now. So again, e to the 0 is 1, and the sine term is going to disappear. And what we'll find is that v0 has to be equal to minus gamma a plus omega b, alright? And from this, if we just rearrange that, you'll find that b, therefore, has to be equal to v naught plus gamma a, but a is x naught, remember? So v naught plus gamma x naught over omega. Okay, so to summarize, our solution for x as a function of t, just plugging in these specific values of a and b that we've now found, x of t is going to be e to the minus gamma t multiplied by, well, a cos omega t is x naught cos omega t, and b sine omega t is going to be v naught plus gamma x naught over omega times sine omega t. Okay, so that's our solution for x of t, given these initial conditions that we have a displacement of x naught and a velocity of v naught. Okay, now let's take the limit of this. So remember that critical damping is what you get when gamma is equal to omega naught, and then the solution has to take a slightly different form. And so gamma being equal to omega naught is the same thing as omega going to 0, right? Because if you look back at this expression for omega that we had initially, omega is the square root of omega naught squared minus gamma squared. So in the critical case, as we approach the critical case, omega tends to 0, right? Because omega naught and gamma are equal in the critical case. So if we want to take the limit of this solution, as omega goes to 0, let's write that out. So the limit as omega goes to 0 of x of t, okay, is, well, we can keep this e to the minus gamma t out the front, and let's think about what happens to these individual terms. Well, the cos omega t term, nothing particularly interesting happens, right? Because we can just plug in omega equals 0 into this cos of omega t, and so we just get x naught times cos of 0. Cos of 0 is 1, and so our first term just becomes an x0. Okay. And how about the second term? Well, the second term is a bit trickier because we've got sine of omega t over omega, and so we can't just plug in omega equals 0 because then we end up dividing by 0. And so what I'm going to do is just add in an extra step here. So I've got v naught plus gamma x naught, and then let's have the limit as omega goes to 0 of sine omega t over omega. Alright, and there are a couple of different ways to evaluate this limit. One of them is to do a Taylor series expansion for sine of omega t, and you would be able to derive the limit that way. What I'm going to do is use L'Hopital's rule, which is what I did in my previous video as well. So have a look back at that if you need a reminder on how that works. But basically we can differentiate the top and the bottom because we've got a fraction, and the top of the fraction, the numerator, approaches 0 as omega approaches 0, but the denominator also approaches 0. And so in that case we can differentiate the top and the bottom with respect to omega, and the limit of that result, the two derivatives are divided by each other, the limit of that is the same as the limit of the original fraction. Okay. And so let's do that. Let's actually evaluate that. That's going to be e to the minus gamma t. So this x0 is still there, and then this v0 plus gamma x0 is still there. So what we want to do is differentiate both of these, both the numerator and the denominator of this fraction with respect to omega. So if we differentiate the top, we're going to get a cos, right? But then from the chain rule, we're going to have a factor of t out the front. And so we're going to get t cos omega t. And differentiate omega with respect to omega, you just get 1. All right. And now I forgot to write in the limit of that, so let me just move that across a bit. And so we want the limit as omega goes to 0 of that stuff there. Okay, now it becomes relatively easy because we can now just plug in omega equals 0, right, to this cos term. And so we are going to get e to the minus gamma t times x0 plus v0 plus gamma x0, and then cos of 0 is again 1, and so this whole limit just evaluates to t. Okay, and you may recall from last video we ended up with exactly the same result, right? This is the critically damped solution. So you can derive that critically damped solution either as the limit of the lightly damped case or as the limit of the heavily damped case, which is quite a nice result. Okay, so that's all I wanted to say about this topic of damped harmonic oscillators for the time being, at least. So I'm going to move on to something else in my next few videos. Hope you've enjoyed this. If anyone watching has any particular requests for physics or maths topics you would like to see me go over, please do let me know. And see you soon in another video.